All right, let's get right into it. Every single day, thousands of ships are out on our oceans, crisscrossing the globe, really forming the backbone of all global trade. But here's the thing. Some of them are carrying a hidden danger. So today, we're going to decode the complex and frankly fascinating world of hazardous and noxious substances at sea. Think about this. Over 80% of all the goods we use travel by sea. It's a remarkably efficient system most of the time. But when a ship carrying chemicals runs into trouble, well, the stakes become terrifyingly high. For the first responders, for the marine environment, a spill isn't just a messy problem, it's a potential catastrophe. Okay, I want you to imagine you're a first responder. A call crackles in. There's a ship in distress. All you know is that it's carrying chemicals. Now, before you can do anything else, before you can even think about approaching that vessel, you have to answer one absolutely critical question. What exactly are we dealing with? Because that answer, it's going to dictate every single decision you make next. Answering that question, it basically turns responders into detectives at a chemical crime scene. The very first step is to start piecing together the clues to identify the threat. So, first things first, we need to know what we're even looking for. The official definition for a hazardous and noxious substance, or HNS for short, is incredibly broad. Basically, if it's not oil and it can cause any kind of harm when it's spilled in the ocean, it's an HNS. And that covers a huge range of things, from flammable liquids and corrosive acids to toxic gases. Now, to narrow that down, responders rely on some really specific classifications. And it's so important to get the difference between dangerous goods and hazardous chemicals. See, dangerous goods are all about the immediate risks during transport. Things that can catch fire or explode. But hazardous chemicals casts a much wider net. It also includes stuff with long-term toxic effects both on our health and on the environment. To get a handle on the threat, every single dangerous substance gets sorted into one of these 9 UN classes. This is really the first piece of the puzzle. It gives responders a quick, high-level snapshot of the main danger. Is it going to blow up? Is it toxic? Is it corrosive? This system is the universal first language of risk when you're out at sea. And this danger is communicated through a really critical visual language. So you might see a pictogram like the one on the left on, say, a smaller container. But that diamond placard on the right, that goes on a big transport unit. They both scream corrosive, but they're part of different international systems that a responder has to recognize in a split second. Digging just a little deeper, we find 2 key numbers. A UN number, like UN 1824, is for transport. It can actually change depending on if the substance is a solid or a liquid. But a CAS number, that's like a unique fingerprint. It's assigned by scientists to one specific chemical substance, like sodium hydroxide itself. Knowing both of these gives responders a much more complete picture of what they're up against. But here's the thing. Just identifying the chemical is only half the battle. Now we get to this really crucial shift in thinking. It's moving from what a substance is to what it's actually going to do once it hits the water. And this graph illustrates the response timeline perfectly. You see, in those first few chaotic hours, the whole response is driven by the immediate hazards. Is it going to burn? Is it toxic to breathe? But as the hours turn into days, the strategy completely shifts. It becomes all about the substance's fate and behavior. Where will it go? Will it sink? Will it just dissolve? That's what dictates the long-term cleanup. To predict that behavior, responders turn to this incredibly powerful tool called the Standard European Behavior Classification, or SEBC. This system looks at a chemical's core properties, its density, how well it dissolves, how quickly it evaporates, and it uses all that to forecast how it's going to act out there in the ocean. So what the SEBC does, which is kind of brilliant, is it boils down all this complex chemistry into 5 simple categories, each with its own letter code. G is for gas, E is for evaporator, F is for floater, D for dissolver, and S for sinker. Just by knowing that one little code, a responder can immediately visualize what the future of that spill is going to look like. It sounds simple, but the implications for planning the response are just massive. So this is the crucial point, right? How do responders take this alphabet soup of codes and numbers and turn it into a concrete plan of action, one that actually protects people and the environment? This is where all that data comes together in a very disciplined 3-step assessment. Step 1, gather all the information you can. Step 2, identify the hazards. And step 3, assess the risk. It's a really structured approach that's designed to cut through the chaos of a crisis and create a clear path forward. So let's see how this actually works. If the SCBC code tells you the substance is a floater, that's an F, then the playbook is pretty clear. You send out vessels just like this one, with booms to contain the spill on the surface and skimmers to physically recover it. It's a physical battle against an enemy you can actually see. But what if the code is G for gas or E for evaporator? Well, suddenly you're fighting an invisible threat. And the priority shifts completely. Now it's all about using computer models to predict where that toxic cloud is going to drift. It's about establishing safety zones, evacuating people, and warning other ships downwind. 2 different codes, 2 totally different responses. Now let's zoom out for a minute, because no single country can handle these kinds of incidents on their own. This entire system of classification and response is supported by a global safety net, one that's been built up over decades of international cooperation. You have organizations like the International Maritime Organization that create the global rulebook. They set up conventions for everything from vessel safety to pollution prevention. And this ensures that everyone, everywhere, is speaking the same language. These are the frameworks that allow countries to work together on a response when a spill crosses borders, creating a unified front against a shared threat. So, from a simple UN class to a behavioral code, this entire system is designed to turn deadly uncertainty into decisive action. But as the sheer volume and the complexity of chemical transport keeps on growing, it leaves us with a really vital question. Is this intricate global safety net we've built actually strong enough to handle the next major disaster?